Hi everyone, welcome back to our discussion. We're talking today about Taylor series in section 11.8. This is the last chapter that we're going to be talking about in the text this semester. So let's do so. You see here the Taylor polynomials that we described in the previous chapter. Remember the idea there is we were essentially given a function f of x, so we had some function f of x, here it is, and we were building better and better approximations to f of x. So we could build a straight line approximation like that touches only at the point A and has the same slope as the function at that point, but then after that it's doing something crazy, something different. Or we could build maybe a quadratic approximation to the function, which has the same first and second derivatives. Or we could build a cubic approximation to the function, which maybe is just a little bit better even, and then, it's going to go and do cubic things. But the idea is we could build any degree polynomial we want, and we had this formula for the nth Taylor polynomial, and it's an nth degree polynomial that's a really good approximation to the function near the center. And in this case, the center was at x equals a. So that was our goal in the previous section. What we're going to do in this section is say, well, instead of using an nth degree polynomial, now that we know so much about power series, infinite series, we can just take this last term and say, why stop there? Why don't we just keep going? And that gives us what's known as a Taylor series. This is a power series, and it's centered at C in this case is the notation the book uses. For some reason the Taylor polynomials were centered at A, but then once we got to Taylor series, which is this just unending infinite series, this is now centered at the point C, and you can see it's got the same form. The coefficients are the same. We derived these coefficients in the previous section, so they're the same coefficients. We just keep doing it forever. And so there's the nth coefficient, and it's multiplied in the power series by x minus c to the power of n, where c is the center. This is exactly the form we've had before. So let's talk about these power series. The important thing now that we've got, though, the thing that we've got about these Taylor series is we know how to build the coefficients. Right? In the earlier sections when we were talking about power series, we could get power series for particular functions by playing around with maybe the geometric series, but we didn't know how to build the nth term. Right? Remember we said, well, a power series looks like this. It's the sum of those terms. There's a general power series, but we didn't know how to find that nth term given a function. And now if you give me a function and it's infinitely differentiable, I can differentiate it forever, then I know how to build the terms, and that's the idea here. So let me show you how this works in practice. So we see here again the Taylor series centered at C, and remember in the previous section we defined the idea of a Maclaurin polynomial. Well, in this section we're going to talk about the Maclaurin series, which is an infinite series, goes on forever, and it's just a Taylor series centered at 0. Our Maclaurin polynomials were Taylor polynomials centered at 0. Maclaurin series is just a Taylor series centered at 0. So everywhere you see a C in this formula has just been replaced with a 0 in that formula. So let's start by finding the Maclaurin series for just the exponential function. And exponentials are maybe our easiest example because, well, we know the derivatives of f of x. Let's use this space. If f of x is e to the x, what I need to know here is f of 0, and f prime of 0, and f double prime of 0. So f prime of x, the first derivative, well, that's e to the x. And f double prime is just e to the x, all the way down, right? The nth derivative of e to the x is still e to the x. So I can calculate these numbers I need. F of 0, well, that's just e to the 0, which is 1. And similarly, every single one of these derivatives is just 1 because I want the derivative at the center, and the center is 0. So every single derivative I calculate here at x equals 0 at the center will be 1, and that gives me all of these terms. And so we can start writing out the Maclaurin series for e to the x. It's going to be f of 0, which in this case is e to the 0, which is 1, plus f prime times x, plus f double prime at 0, which is 1 over 2 factorial x squared. And the next one's f triple prime, which is 1 over 3 factorial x cubed. The next one's the fourth derivative, evaluated at 0, which is 1 over 4 factorial x to the 4, plus ... This continues forever. And so there is our Taylor series for the exponential function, right? This is just e to the x. Here's the Taylor series for the exponential function centered at 0, also known as the Maclaurin series. And you can see this one is particularly simple. We can write it very easily. If you look at the general term here, the power of x and the factorial are always the same. So this is going to be x to the power of n divided by n factorial, a sum from 0 to infinity, because remember that n factorial is the product of the first n numbers, integers. 0 factorial is defined to be 1, 1 factorial is 1, 2 factorial is 1 times 2, and so on. So if you write that series out, you'll find it's the exponential. So it's a very simple series to write down, but that gives us our first Taylor series for a function. And this is essentially how we go about finding all of our Taylor series. When we're doing this, we're always going to build all the derivatives, evaluate all the derivatives at the center. Look, every single one of these needs to be evaluated at the center, and then just plug it in. And you can see coming directly from that formula there, or this formula here, in this case, every single derivative was equal to 1, so all of those are just 1. So we get 1 times x to the n over n factorial, which is what I guessed down there. Let's pause for a second, think about what this means. Here we've got a Taylor series expansion, right? We've got a Taylor series expansion for a function. For example, we just showed that the Taylor series expansion centered at 0 for the exponential function was this, which we could also write very simply like that. The first theorem here says that if you give me a power series, if I come along and say this is a power series for the exponential function centered at, well, in our example, the center was 0, and the radius of convergence we didn't calculate, but I'm about to. If I've got a power series, then that power series is the Taylor series. Here's another example. Remember, we know from the previous section that the geometric series sums to 1 over 1 minus x. So if we take this simple function, 1 plus 1 over x, we can write down a power series for it. And what this theorem is saying is that this is the Taylor series. All right? We derive this series some other way, but the fact that we have a power series with a center and a radius of convergence, remember the center here was 0 and the radius of convergence was 1 because x converged, the series converged when the absolute value of x is between 0 and 1. As long as we've got something of that form, then the series we're looking for is a Taylor series. And what that's telling us, in other words, is it's telling us what these numbers are. In the first case, that number is 1. In the second case, that number is 1. In the third case, that number is 1, because I've got a 1 in front of the power of x there, right? So if I had sat down and calculated all of those derivatives and divided by n factorial, I would have found those numbers 1. These coefficients would be exactly the same if I found this series roundaboutly by finding all the derivatives, right? Rather than saying this is a geometric series, if I just found the derivatives here, then I would have found exactly the same series. That's what this Taylor series theorem is saying. It's saying that the Taylor series is the representation as a power series of the function. So if you have a power series, it is the Taylor series. So it's pretty powerful. Let's pause for a moment before we do another example and think about the radius of convergence of this exponential function. So we found the Taylor series for e to the x, and we want to know the ratio of convergence, the radius of convergence. And the way to do that is almost always to use the ratio test. And so we need to know the nth term. And that's why it's important to be able to look at a series and write down the nth term. Write down that this is x to the power of n divided by n factorial. You should be able to go backwards and forwards between those two representations. Can you write it out in the sigma notation? Can you write it out as a series? Because then we're going to look at the limit as n goes to infinity of the ratio of terms. And in this case, it's going to be a sub n plus 1 x to the power of n plus 1 divided by a sub n x to the power of n. And this is exactly what we were doing in the section on power series. So we're going to take that n plus 1th term, which in our case is x to the power of n plus 1 over n plus 1 factorial. And we've had some practice at this recently, right? This is what we've been doing, over n plus 1 factorial. And we're going to multiply it by 1 over this term, which is n factorial over x to the n. And then we've got to simplify that. We cancel the like terms, so we go through this and say, well, we've got x to the n here and x to the n there, they cancel. That leaves us an x on the top. And then if we think about the other terms, this is n factorial, which is the product of the first n integers, divided by n plus 1 factorial, which is the product of the first n plus 1 integers. And when we do that, we can cancel the first n of them. And so that leaves us with the single factor n plus 1 in the denominator, and we need to take this limit, and this limit is going to be 0 because x is a fixed number. Whatever value of x we're looking at, this limit is just a fixed number divided by something that's getting larger and larger. That goes to 0. That's less than 1. So that tells us that this Maclaurin series converges for all values of x. Right? It didn't matter what x is, as long as x is in the domain. This makes sense, and that limit will be 0, which means it converges. So this power series is valid for all x, which means our radius of convergence is infinity. Right? Our radius of convergence, this is a power series, so it always converges in the interval c minus r to c plus r. The center in this case was 0, and so our interval of convergence is all x, which is minus infinity to infinity. And so we take r to be infinity, and that gives us our radius of convergence. Let's look at another example. This time we want to find the Maclaurin series for cosine. The Maclaurin series are really important, so that's where we actually see a lot of them. So our function here that we're dealing with is the cosine of x, and what we're going to want to know is the cosine of 0. In other words, we're going to want to know f of 0. And then we're going to calculate f prime, and f prime, as you know, is a negative sign. And then we're going to want to calculate f prime of 0, and we can do those things. The first one, cosine of 0 is 1. Sine of 0 is 0, so we keep going. The second derivative is minus cosine of x now. And so the second derivative is going to be minus 1 when x equals 0, because cosine of 0 is 1. And then we calculate the third derivative. The third derivative is back to positive sign because we're differentiating cosine again. We calculate the third derivative at 0, and we get 0 again. One more derivative. You know, we keep doing this forever. It's fun, isn't it? We keep doing this, we get the fourth derivative, it's cosine of x. The fourth derivative, let me put this in brackets there, the fourth derivative at 0, cosine of x is 1, and then the next derivative must be negative sine. In other words, this whole pattern repeats because we're back to cosine. So we've got a cosine, then a negative sine, then a negative cosine, then a sine, then we're back to cosine, so a negative sine, negative cosine. It's got to repeat from here, which means the values repeat as well. Right? So these four values are going to repeat for all time because we're just cycling through these derivatives. It takes 4 derivatives to go from cosine back to cosine. And so we're going to get 4 terms that then repeat forever. So we could start writing out the series. Just looking at this formula, we're going to get 1 plus no x. Right? I'm just plugging in 1, 0, minus 1, 0. So 1 plus no x. The next one is going to be minus 1 over 2 factorial x squared. The next one's going to be 0 over 3 factorial x cubed. That's the third derivative. The next one's going to be positive again. It's going to be 1 over over 4 factorial x to the 4. And the next one's going to be 0 over 5 factorial x to the 5 plus minus 1 over 6 factorial x to the 6 plus 0. You get the idea. It's worth writing out all of these things at least the first time to see what's happening, and then they're going to repeat again. So putting this together, the only ones that are there are the even terms. 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the power of 4, and then minus 1 over 6 factorial x to the 6. This pattern tells us the next one's going to be 1 over 8 factorial x to the 8. Keep writing out those terms and you'll see that's the case. And so we get a Maclaurin series for cosine. And remember, what we know about cosine is this is an even function. Right? It's an even function. Think of the graph. It's reflection symmetric around the y-axis. Well, this is an even polynomial. It's written in terms of even powers of x. X to the 0, x to the 2, x to the 4, x to the 6. The very fact that this is even tells us that these need to be even powers of x. If you think about sine as an odd function, that means sine must be written in terms of the odd powers of x. So let's try and get together a nice form of this expression, and then we'll look for the radius of convergence. So here's our series, 1 minus a half, well, it's a half at 1 over 2 factorial, and so on. We want to write this as an infinite series, usually starting at 0 and going to infinity is a good way to go. You can see the powers of x here are x to the 0, x to the 2, x to the 4, x to the 6. You can see that this is alternating. So we're going to have a minus 1 to the power of something when n is 0, when the x power is 0. So if I put an n there, x to the n will be 0. X to the 0 will be 1. And I want a positive, so I'm going to make this an n as well, because then that will match. Minus 1 to the 0 is going to give us 1. But I'm only getting the positive numbers here, right? X to the 0, x squared, x to the 4, x to the 6. So I'm going to put a factor of 2 there. So then when n is 0, I'm going to get x to the 0. When n is 1, I'm going to get x squared. When n is 2, I'm going to get x to the 4. So I need this 2n there to only get the even powers of x. And I need to balance that with the denominator here, which is also the same number. So 2n factorial. 1 factorial, well actually 0 factorial, 2 factorial, 4 factorial, 6 factorial. This will produce it. So there's our nth term for cosine. Now we again need to look for the radius of convergence. And to do that, we use the ratio test. In the ratio test, we need to look at consecutive terms, right? One term after the other. I'm going to write the general form like this. So then the next term is going to be a sub n plus 1, x to the power of 2 lots of n plus 1, divided by the current term, which is a sub n, x to the 2n. So this is the current term. Drew that badly. But there's the current term. And then the next term is just going to replace both n's with n plus 1. And then we're going to take the limit. So this is the limit in this case of a sub n plus 1. Well, I'll just write out what it is. That's minus 1 to the power of n plus 1 times x to the power of 2 lots of n plus 1 divided by 2 lots of n plus 1 factorial. Well, it's the factorial of that whole thing, so be careful about that. And then I'm going to multiply here by the reciprocal of just this term, this in other words, which is going to be 2n, factorial of that whole thing, divided by, well, I've got minus 1 to the power of n, and then we've got x to the power of 2n. And so let's simplify this, and we'll start by just saying, I'm going to get rid of all of the minus 1s because there'll be 1 left after the cancellation. But that doesn't matter because I've got absolute value signs there, right? So those absolute values are going to eliminate any negatives, and we're going to end up with cancelling some of the powers of x. We've got x to the power of 2n there, plus 2. This is 2n plus 2, and I'm going to cancel 2n, so those are going to go. I'm going to be left with x squared. And then I'm going to think about what's left here. This is 1 times 2 times 3 times 4, all the way up to, what's the number now? Well, the last number in this list is 2n. So if n is 12, the last number in that list would be 24. But on the bottom, I go all the way up to 2n plus 2. So that's going to be 1 times 2 times 3 times 4, all the way up to 2n, and then 2n plus 1, and then 2n plus 2. There's more terms going on here, precisely because this thing is 2n plus 2 factorial. So it's all the numbers from 1, all the positive integers from 1 to 2n plus 2 multiplied together. And now we're going to cancel a bunch of stuff. There's the fun part about factorials. We're going to cancel all the numbers up to 2n. So all the numbers up to 2n actually now leave us 2 terms in the denominator, which is fun. This is the limit as n goes to infinity of x squared over those 2 terms. 2n plus 1, 2n plus 2. Cool. The thing is, x squared is a finite number, and this thing in the denominator still goes to infinity, goes pretty fast, so that's going to be 0, which is less than 1. So the radius of convergence here is all real numbers x. So the radius of convergence is infinity. Sorry, the interval of convergence is all real numbers x, because the interval of the radius of convergence is infinity. The interval of convergence is all real numbers. Because it doesn't matter what x is, this power series is going to converge. This power series is our Maclaurin series, and so we've got our final result. So summarizing that, what we see is that the cosine is given by this Maclaurin series, and it converges for all real numbers x. So similar to the exponential function, cosine converges everywhere. So what we've seen is a couple of important Maclaurin series. We've seen one for the exponential, we've seen one for cosine. And we could equally well build one for sine. You see it down here. Like I said, it's built out of all of the even terms. So you notice there's a lot of similarity between these three series, because this is an alternating series, but it's only even terms. Sine, which I encourage you to sit down and work out, notice it uses odd numbers. 2n plus 1 is always going to be odd, in the same way that 2n is always going to be even. And so this looks very similar, right? This is x to the 1 over 1 factorial minus x cubed over, it's all the odd ones. Whereas cosine has the same general form, it's even, and these two are alternating, right? They're alternating series. And the exponential has even and odd terms, 1 plus x squared over 2, so this is a 1 factorial, x cubed over 3 factorial, so very similar, except this isn't alternating. These are all added for the exponential function. For the cosine, we've got an alternating series which is even. For sine, we've got a very similar alternating series, but it's odd. There's a connection between these, and we'll come back to that maybe next time. But before we end today, let's look at a more general Taylor series that isn't centered at the origin. So this time we're going to find the Taylor series for f of x being 1 over x centered at the point x equals 2. We obviously couldn't build a Maclaurin series for this function. The function's not defined at 0. The derivatives aren't defined at 0. But we can build the general Taylor series centered somewhere else. So in this case, we'll center it at 2. And I'll follow the book, and I'll call that a c. So our c value here is 2. And as you'll recall, what that means is finding the value of the function and all of that function's derivatives at x equals c, in this case, 2. So our job is just to set off and calculate the function and all its derivatives. We know the function is 1 over x, and we know the first derivative of 1 over x is minus 1 over x squared. The second derivative, the minus 2, is going to come down now, so it's going to become positive 1 times 2 over x cubed. And as you're doing this, write out the numbers, because the numbers will help you. Don't simplify them, because you'll lose what's going on. Now the minus 3 is multiplying. So we have a 1 times 2 times 3. If you started writing that as 6, you might quickly forget why the 6 was there. The next one, that 4 is going to come down and become positive 1 times 2 times 3 times 4. And now we're positive again, because we were multiplying by the power, which was x to the minus 4. And that suggests that the nth derivative is, well, the fourth derivative had a 4 factorial on the top, so the nth derivative is going to probably have an n factorial on the top. It has one higher power, so x to the power of n plus 1, and then we've got minus 1 here that's alternating, and noticing that when n is odd, so in this case n is 1, the first derivative, I get a negative, and then the second case, when n is even, I get a positive. So I can just put an n here, the odd powers will make this negative, and then the even powers will make it positive. So all we need to do now is evaluate these various things at the center where x is 2. So f of 2 is 1/2, and then the derivative at 2 is minus 1 over 2 squared, and the second derivative at 2 is 2 factorial over 2 cubed. Right, I'm just plugging into these expressions. The third derivative, evaluated at 2, is minus 3 factorial over now 2 to the power of 4, and so on. So we can use this general form that we've come up with already to say that the nth derivative, evaluated at 2, is going to be n factorial divided by 2 to the power of n plus 1, multiplied by that alternating number, x to the power of n. So these together are all going to allow us to build the Taylor series. So let's write it down. So using these values, we could go straight ahead and write down this general term because we've got the coefficient there. But let's write it out just to get a feel for what's happening. Right? This is f of 2 plus f prime at 2, x minus 2, because the center is 2 here, plus the second derivative at 2 divided by 2 factorial, x minus 2 all squared, and then the third derivative, let me just write that out, at 2 divided by 3 factorial, x minus 2 cubed, and then so on. And writing these things down, we've got all the values there. First one's a half. The next one's minus 1 over 2 squared. And then we have to divide by 1 factorial. I didn't write it there, but there's a 1 factorial happening here. X minus 2. And then the next one's the second derivative, which is 2 factorial over 2 cubed, and then we're going to divide that by 2 factorial, x minus 2 squared. And then the next one is 3 factorial divided by 2 to the power of 4, and then all of that's divided by, this is coming straight from the formula, right? There's a factorial in the formula. This is 3 factorial, x minus 2 cubed. And then the next one's going to be 4 factorial over 2 to the 5 divided by 4 factorial, x minus 2 to the power of 4. And then the next one's going to be negative again. You hopefully can see how this is going. I don't need to have written all these terms down because the pattern's pretty clear, and we've got the general term anyway, and that's going to continue forever. And so simplifying, what you see here is that the factorials are cancelling, right? There's a 1 factorial here, which is just 1 anyway. The 2 factorials cancel, the 3 factorials cancel, the 4 factorials cancel, the 5 factorials cancel. They all cancel, so we're left with a half minus 1 over 2 squared, x minus 2, plus 1 over 2 cubed, x minus 2 squared, minus 1 over 2 to the 4, x minus 2 cubed, plus 1 over 2 to the 5, x minus 2 to the 5, minus dot dot dot. Sorry, yeah, did I lose a sign there? No, I left a power. That should have been a 4. Minus dot dot dot. So there's our general series. I could then encode it like this, or I could use our nth term here to write it out equally well. 1 over x is going to equal, well, it's the sum, n equals 0 to infinity, of our nth derivative, right? I'm just plugging in the nth derivative at c. It's n factorial over 2 to the power of n plus 1 minus 1 to the power of n, x minus 2 to the power of n, and all of that's divided by n factorial. So again, I mean, I'm just repeating what I've already done. Those n factorials cancel, so the general expression is going to match what we found when we wrote it out. These are two different ways of thinking about the problem. We've got minus 1 to the n because it's a alternating series. 1 over 2 to the power of n plus 1, x minus 2 to the n, which matches what we have right there, hopefully, if we write it all out. So these are two different ways of looking at our series. The last thing I want to do is find the interval of convergence of this Taylor series. So here's our general form, and again, if we're going to look at the radius of convergence, we need to use the ratio test. So just plugging in the n plus 1th term, it's going to look like 2 to the power of n plus 1, and then x minus 2 to the power of n plus 1, and then I'm going to divide it by the nth term. So flipping those things around, I'm going to have 2 to the power of n plus 1 over minus 1 to the power of n, x minus 2 to the power of n. And just being clear what we're doing here, I've written out, I'm calculating this ratio. This whole thing evaluated at n plus 1, you know, this whole expression at n plus 1, divided by that whole expression at n. And that's going to leave us with what we see here. Again, we're going to be left with a minus 1 when these cancel, but the absolute values kill those anyway. I'm going to have 2 to the power of n plus 1. Plus 1, I've got one more of them in the denominator than I have in the numerator. So I'm going to be left with 1 in the denominator there. So there's going to be a 2 to the power of 1 in the denominator. And then when I cancel the n, x minus 2 to the power, I've got n of them there, and I've got one more of them there, so I'm going to be left with 1 in the numerator. And you'll notice, in this case, there are no n's left. So that limit actually goes away. What we've got here is a half of x minus 2 absolute value. I can just factor that half out the front, and that has to be less than 1 to converge, right? If this power series is going to converge, then this quantity has to be less than 1. There's no n's, so the limit's just gone. So I can say that this Taylor series converges when, well, just multiplying both sides of that by 2, right? Because I've got x minus 2 is less than 1, a half of that is less than 1. So I've just doubled everything. If I multiply left and right by 2, we end up with that. And so as long as x is in that region, well, what does that region look like? That region is centered at 2. Here's the center. It's always centered at 2. And here's the radius. So we start at 2 and we go 2 to the left. This is 2 plus 2. And we go 2 to the right. The other way around. This is 2 minus 2. So this is 0 and this is 4. So this series converges in a region centered at 2 with radius 2. So it's converging in this region. Now what happens at the endpoints? If I put x equals 0 in here or x equals 4 in here, the 2 to the n's cancel and we have divergence series. You can check that, but these things diverge when x is equal to 0 or 4. In other words, it diverges at the endpoints. I wrote 0, but I meant 4. It diverges at the endpoints, and so that means that the interval of convergence is between 0 and 4. And that's what we wanted to know. We've got a radius of convergence of 2 with an interval of convergence centered at 2 and with a radius of 2 in each direction. These are pretty long problems sometimes. Thanks for tuning in for this one. We will do more tomorrow. Have a great day.